So good afternoon, everyone. My name is Anjali Bamzai, and I am on a 2-month stint as Embassy Science Fellow at the US Embassy in Cairo, Egypt. I want to thank the hospitality of CCIC staff for hosting me here at their center. Today, we have Wassila Thiaw, our colleague, Dr. Thiaw from CPC, Climate Prediction Center at NOAA, National Centers for Environmental Prediction. Wassila is the head of the international desk there, and he works with forecasters from all across the globe. The topic today is forecasting climate extremes to advance early planning in Africa. We are grateful to Wassila for joining us. It's 7:30 a.m. his time. So good morning, Wassila. Thank you for your time and expertise. Wassila has a PhD from University of Clermont-Ferrand in France, and he has had his early education in Dakar, Senegal. He is a fellow of the American Meteorological Society. It's a very prestigious award to be fellow. And in 2019, he got a special award from American Meteorological Society for sustained efforts in providing services leading to reducing risks around the world. Also, more recently, Wassila has been working on health issues, human health and environment, and he is part of the GeoHealth initiative at the American Geophysical Union. So what I'm going to do is I'm going to turn it over to Mr. Chuck Fee to say a few words. He is the Econ Officer at the US Embassy. And then Dr. Ala Khalil from our Drought Early Warning System here at the CCIC will also say a few introductory remarks. And after that, Wassila will start his presentation. Thank you, Wassila, again.
Over to Chuck Fee.
Hello, everyone. This is Chuck Fee from the U.S. Embassy. Thanks for joining us today for our 6th speaker. We'll be talking with Dr. Wassila Thiaw about forecasting climate extremes to advance early planning in Africa. Dr. Wassila is a U.S. expert from the National Oceanic and Atmospheric Administration in Washington, and is a world-renowned expert on climate and agriculture issues. We're very excited for him to be here today, and really thank him especially for waking up so early to talk to us here in Cairo. Hope everyone finds this interesting. I can imagine so, given that it really crosses exactly to climate and agriculture, the kind of stuff we're working very hard with in our cooperation with the Climate Change Information Center. So thanks to Dr. Allah, from my office, to Dr. Wassila and Dr. Anjali for making this all possible. And I hope you enjoy it. Thanks.
Thank you so much, Chuck. Over to you, Dr. Ala.
Okay, thanks, Chuck, and thanks, Dr. Angela, and welcome, Dr. Wassila. Welcome to all of you. I am Ala Khalil, Supervisor of Early Warning Unit in the Climate Change Information Center. And on behalf of Dr. Mohammed Fahim, Chief of Climate Change Information Center, I'd like to thank the US Embassy for supporting us and for the weekly presentation and seminars. I hope all of you during this presentation increase your knowledge and information about the forecasting climate extreme. Actually, I am waiting this presentation from the first day of the seminar. I am interested to listening to Dr. Wassila, because all of us agree that the subject of forecasting climate change and extreme is one of the most important things in our life, especially in agriculture sector. Thanks again for you, and I would like to give the word to Dr. Wassila to learn from him. Thank you.
Thank you very much, Dr. Ala. Thank you, Dr. Bamzai and Julie, who I actually have known for now more than 25 years. Really, I'm very, very humbled that Anjali reached out to me and asked me, to give this presentation today. I'm really, really very excited to meet you all. And I know that some of my colleagues also who work at the Egyptian Med Authority are here with us today as well. So I really take this as an opportunity. So I'm gonna go ahead and share my screen and then we're gonna get started. So it should be coming, I hope. Please tell me if you can see my screen.
Yes, we can, Dr. Wassila.
Wonderful. Thank you very much. Forecasting climate extremes to advance early planning in Africa. I am a meteorologist, as Anjuli has introduced me, and really the use of meteorological information to advance early warning and early planning is really something that is dear to me. I just have it in my heart, and also coupling that with capacity development, especially in the developing world and also in emerging countries as well. So at the end of the presentation, I would like to acknowledge my colleagues who work with me very closely, Andalk Bekele, Lishu, and Vanlamani Kumar, and Rob John. Some of them contributed to some of the slides that I'm going to be showing here. So I would like to acknowledge them for that. The topic is about, advancing early planning and early action in Africa. So I'm going to start with this picture here that was produced by Neil Hayes and published by Imam Gash of Visual Capitalist. So this really tells it all about global warming, doesn't it? So we can see that since 1880, the Earth's average surface temperature has risen by about 0.07 Celsius every decade. So that's a lot. And the rate of temperature change has also grown, more than doubling to 0.18 since 1981. And you can see here from this diagram that really this warming trend has been increasing. And you can see that red mean higher temperature changes, and you can see that clearly the last 5-7 years now that in 2022, has been warmer than ever before. So that is really, really, really telling. Global warming is the reality. It's something that the data show us. So we're not talking about what causes this global warming, but it is there because that's what the data show us, and there is consistency across the board in terms of temperature analysis. Now, this is my own figure, of course, produced by some of my colleagues who work with me, but this is the evolution of global air temperature. Just trying to place here Africa in the context of this global warming. So the red time series is the global temperature, average global temperature, and then I take different regions of Africa. The Sahel, Eastern Africa, Northern Africa, Southern Africa, and then Africa as a whole. And you can see that the global, the Africa temperature change just follows the global trend as well. And if you just focus on Northern Africa, you can see that the brown curve can see clearly that there is the increased trend in temperature change in Northern Africa, consistent with what we see in other parts of the world as well. So this is nothing new. I think that we all know about this. I just wanted to show this as a starting point. So what takes me? So with this global warming, what is it that we have observed? We have observed that heat waves are increasing in both intensity and duration over Africa, and that's something that actually the IPCC report tells us, even though the data also does show it very clearly. but the problem is that Africa has a population highly exposed to sunlight and extremely vulnerable to extreme heat. And with that, though, there is little awareness that extreme heat is a high impact weather or climate phenomenon, and there is no heat action plan at this moment. People just go out under the sun, do their work, to the market, to the field, without realizing that actually they are really exposing themselves to danger. So extreme heat events are not routinely monitored in most countries in Africa, actually in the developing world, and heat-related illnesses and deaths are not systematically reported, actually, if any. So this lack of reporting results in gap in knowledge, knowing the threshold that trigger heat-related mortality. So what is it that we do about this? WMO created the Global Framework for Climate Services, and health is one of the pillars of the GFCS. So my agency, NOAA, is contributing to advancing actionable climate forecast as a contribution to this great initiative that WMO has created. So, so we're trying to really advance heat wave forecasting, but also how do we really make sure that this information is available to the public, to the decision makers, community organization to reduce impacts of heat on human health. So this is just an example of the average number of heat waves looking at the 2015-2018, and you can see very clearly that during this period from July to August, the summer season, heat wave is quite prominent in Northern Africa, in the western part of Northern Africa, but also in the eastern part, and here's Egypt here. But you can see that the average number of heat waves go from 3 to 6, about 6 heat waves on average. So we can talk about the definition of heat wave here, just in this time. What we're talking about heat wave, we're looking at heat index. Heat index is a combination of temperature and relative humidity, and we're looking at heat index values exceeding 40 degrees Celsius here for 3 consecutive days. So that's what would qualify for a heat wave event. So that's a little bit extreme because we talk about 40 degrees Celsius, but we talk about a combination also of temperature and relative humidity. So the same map that I have shown before, reproduced here, and then here, this, by the way, is these histograms were produced by Ms. Amira Nasser from the Egyptian Met Authority when she was visiting with me at the African desk a few years ago. So so we looked at it, and you see that this is the station of Aswan in Egypt, clearly showing that heat waves are more prominent, frequent during the summer season, averaging here about 2.5 heat wave event for the month of June, and a little bit more than 2 in August. And we look at also the distribution of heat wave, and we can see that the heat wave are more frequent in the southern part of Egypt. As you can see here, these stations here, you have where there is more frequency of heat wave than in the northern part of Egypt. So clearly, then heat wave is something that we are observing based on our definition of heat waves, and we can look and see now that heat waves are definitely present. How can we predict those heat wave events? So this is just an example of a heat wave event during the week of 7 to 13 August of 2015. And again, I would like to acknowledge Amira Nasser because this work was done while she was visiting again with my team in the African desk. And you can see here, this is the top panel on the left is the observation from the era interim. And the bottom panel are different models, ECMWF, NCEP, and the UK Met Office. So the observation clearly do show a prominent heat wave during this week of 7 to 13 August of 2015, but also the models were able to depict somewhat, this heat wave, especially over the southeastern part of Egypt, as it is evident here in the ECMWF, but also in the UK Met Office, a little bit less for the NCEP model, but this is just one event. So clearly, what it tells us that the models are able to depict this heat wave event, and this is about 8 days, 1 day lead. Now, what I have shown you there is just one 1 week event here, but we have gone back and looked at these heat waves, and this is the performance of the models. And here we're looking at the NCEP model, the Global Ensemble Forecast System, in blue, and in orange is the Climate Forecast System version 2. So here we're using what we call area under the rock curve, relative operating characteristic, to measure the performance of the model. And what we're looking at is skill values higher than 0.5. 0.5 is just a random forecast. So the higher the value is going toward 1, the more performing the model. So looking at the rock for heat index exceeding 4 degrees Celsius, this is for Northern Africa as a whole. So both models, both the NCEP CFS version 2 and the Global Ensemble Forecast System performed about 0.63, which is really quite a good skill in terms of predicting heat waves. And actually, we do have also, skill scores that are very comparable for other regions, like, for instance, the Sahel during the spring season in March, April, and May. So this tells us that heat waves are quite predictable, and this is understandable because temperature is in general more predictable than rainfall, for instance. So based on that, we are working now on trying to issue global heat hazard outlooks. So this is just an experimental product that we actually started only last month. And shaded areas are where maximum temperature here is expected to rank within the 5. This is the dark brown. 10, that is the red, and 15 excessive heat, most elevated temperatures in the 30-year period from 1991 to 2020. So in meteorological term, we would say that the 95th percentile, the 90th percentile, and also the 85th percentile. So so this is something experimental. We haven't brought it to operation yet, but we are moving toward that. So we're also working on developing urban heat island forecasts as well. So this is just an example of an urban heat island forecast from August 16 to August 20th, looking at Northern Africa. So this is another way to issue heat alerts for particular locations in different parts of the world. So what we're looking at here is the maximum temperature and the rainfall. And we look at the 80th percentile here. We look at the climatology and we assess, is the model saying that the maximum temperature is going to exceed the climatic percentile If yes, then we say, okay, we shade in brown, that is, the Tmax is favorable. If there is rain, or no rain means that also conditions are favorable. So if those two conditions are met, then we issue an alert, and that is the red that you see there. So this is also quite experimental, that we also started to do over the past 3 months or so. And then we put this legend so that people can have a good explanation of what we're doing there. And then so that leads us to this interactive map where you could really access this information on heat waves. We have here a menu where, you know, over the next 3 to 7 days, if heat wave, if for Tmax is going to be exceeding the 80th percentile or the 90th percentile, and we can have also week 2 to 4, and also for the 80th percentile, also the 90th percentile. So when you click there, the map will display and will show you all the stations that meet the requirements. So it is interactive, and I'm going to do just a quick demonstration here with this web link where you know, people can just click. It's not available. It's not made available to the public yet. But once it becomes operational, it will be. We're still adjusting. But then here within Egypt, we can just go to any station in Egypt, and we click here, for instance, and that's Giza. And then if you click on Giza, then if there is an alert, you will see that. Actually, if there is no alert, you will not see the station. You will see the station displayed only if there is an alert. So you can see here the condition that for August 25th, for instance, there is no alert, but there is one for August 26, 27, 28, and 29. So we're hoping that this information is going to be useful to the public, to the decision makers also as well. You know, given that a few days in advance, they will be able to at least have an indication of where heat might be a problem based on this condition. And of course, like I said, we are still in the process of revising this and improving it before we bring it into operations. So why are we doing all of this? Interesting, because what happened was that, as I said at the outset of this project supporting the Global Framework for Climate Services, and we knew that there was a demand from the health sector for climate information. So we did a workshop in Senegal, and I'll show you a little bit a picture of that workshop in a minute here. But we did a workshop, and they said, well, you know, really, infectious diseases is very important, but heat wave is really a problem for us. So we say, okay, let's go and take a look what we can do. So that's how we really started to look at predictability of heat waves and assessing our models in terms of predictability, performing in heat wave forecast, and see if this is something that we could provide to communities. So that's how we really came to develop, to start developing this pilot project on end-to-end heat health early warning. And this is the schematic here that we're using for enabling heat health early warning. And this is actually work that I have published, that is accepted in the Bulletin of American Medical Society, and it is in press, should be coming out anytime soon. So from a heat wave forecasting tool that we have developed, we can make the forecasts, but that is not enough. We have to work with the social scientists who have livelihood data and good knowledge of this livelihood data and population vulnerability. So we then bring the communities, the meteorologists and the social scientists together to co-produce health impact outlooks by integrating the socioeconomic factors into the forecast using geographic information system. So that help us prepare a heat health early warning bulletin that now can be used to for public intervention. So really it is as simple as that, but it requires multidisciplinary effort where you have the climate forecasters working together with the health professionals. And when I talk about health professionals, I'm not just talking about medical doctors. I'm talking about everybody who's involved in following health and economists and everybody in local authorities who really can convey information to communities to help reduce health risk. So this is just a snapshot of that workshop that really started all of this that we did in 2019. And you can see the expertise from the health sector, communication, environmental health, the medical doctors, health economists, social scientists, and social workers who were part of this group that you see here that really helped us develop a prototype for translating the heat wave forecast into health early warning system. So obviously the tools, forecasting tool are essential. It's the basis of any climate weather-based early warning system. So this is the our forecast procedure here, where we look at I'm not going to go into detail in this. You can see this, the heat wave forecasting tool. We look at the circulation. That's really the meteorology. That's the job of the meteorologist. So if you're not a meteorologist, you don't have to worry about it. We use this the forecast of the circulation, but also we look at the post-process tools for the temperature and also the heat index. Of course, we use the observations as well to verify this forecast. I talked about the relative operating characteristic and the area under the rock curve that we use. We also use Heidegger-Silk score to evaluate. So all of this feed into what we call a heat hazard outlook. So that is a heat hazard outlook that is now integrated with the socioeconomic factors in order to produce the heat health early warning bulletin. So we have this website that is operational, real-time available, and I'm gonna just click on it quickly to show you these tools and if it can come. So here we have the heatwave forecast tools for Africa. So again, this is for meteorologists that they can go ahead and take a look at it. There are various products, and our partners in the Sahel, where we really have started already using this during the heatwave season to make their own heatwave forecast. So, so this is the heat hazard outlook at week 2 that I have talked about. So we use convergence of evidence between the circulation forecast, the post-process forecast, and we use geographic information system so that we can have the shapefile to depict areas where heat wave might be a problem. And so the shapefiles can be translated to the health professional who can do the integration with the socioeconomic factors. So now working with Senegal, because you do the forecast, we can do the forecast globally, but to really translate the forecast into early planning or early action for health, we really have to work in local scale. So we have this pilot project in Senegal where we're working closely with the Med Service there, but also with the Ministry of Health, the Red Cross, and also the Center of Ecological Monitoring. So we give the forecast to our West Africa forecast, the one I have just shown, to the Senegal Med Service, and then they go ahead and adjust to Senegal, add value to those forecasts, and then derive these shape files because they're using GIS, and then provide that information to the Ministry of Health, who work with Center of Ecological Monitoring at the Red Cross, to derive this this map here, which is the heat health map that is depicting areas where heat might be a problem, and that we use also to provide alert or advice to communities to try to mitigate the health.
Dr. Wassila, can you hear me?
Vulnerability and map out areas at health risk. The agencies work together to prepare a heat health early warning bulletin. The bulletin features advice for action to be taken to mitigate the health risk. And then the bulletin is submitted via several channels to reach the vulnerable populations. So training is extremely important to this, not only to the forecasters, but also to the health professionals as well. The forecasters need to develop skill in forecasting heat waves. This is quite new. Looking at the tools, making sense of the tool, understanding the post-process forecast, and integrating all of that information to come up with the heat hazard outlook. But also the health professionals, very new to them as well, who need to make sense of this heat hazard outlook and how is that integrated with socioeconomic factors. So we started this. Unfortunately, this was right before COVID that we invited a meteorologist from Senegal and a health professional from rural health to work together. And while they were in the African desk, we made great progress. But unfortunately, COVID hit, and they were the last one to come. So we're trying to, now that COVID is winding down, we're trying to revitalize. And in fact, we have a workshop in Senegal in September to try to continue the training for both the health professionals, but also the meteorologists. Now, enough of heat. I'm feeling even hot myself now. So a little bit of rainfall too. So this is just showing the variability of African rainfall, looking at different regions. This is the Sahel, Eastern Africa, Northern Africa, Southern Africa. And you can see that the Sahel, with this very well-known multi-decadal variability, that definitely triggered a lot of scientific research and inquiry as to why did we have this very prolonged drying trend, in the start in the late 60s into the early 2000s, and then we had a reversal with rain pouring down. In fact, this year it's really, they have record rainfall, in parts of the Sahel. So it's quite a unique climate feature that we don't see anywhere else actually in the world. So we see East Africa here, also definitely showing many years of dryness. Southern Africa, Northern Africa, I think it's quite, the variability is quite interannual, as you can see there. So how do we attribute variability to African climate? So there are several things. Global warming, of course, is one of them. Number one, I would say, El Nino Southern Oscillation, the Indian Ocean Dipole, the Atlantic Multi-Decadal Oscillation, the North Atlantic Oscillation, the Madden-Julian Oscillation, several things that we can really link to climate variability and require a lot of diagnostics to better understand the mechanisms associated with this variability. So I'm just going to talk a little bit about the El Nino Southern Oscillation and what is ENSO. Many of you already may know what ENSO is, but just for some people who don't know what ENSO is, because it's really the dominant climate mode on the interannual timescale. It features warming or cooling of the surface of the tropical Pacific associated with changes in rainfall distribution. So if you just feature the tropical Pacific, warming there in the tropical Pacific plus rainfall surplus is El Nino. Cooling plus rainfall deficits, La Nina. It's as simple as that. It is important that we do have that coupling because a lot of people think that just warming is El Nino. No, we have to have also rainfall surpluses. It's a coupled system, ocean atmospheric system. So these changes in the tropical Pacific affect the distribution of rainfall and temperature around the world. So this is just showing an example of El Nino and La Nina years. So you can see the comparison. So this is the mean temperature during an El Nino year in 1998. And you can compare with the mean temperature during a La Nina year. So you can see that here it is red, here it is blue. So there's a contrast right there, quite a sharp contrast between El Nino and La Nina. And if you look at the departure from normal, you can see that on average during El Nino, you have warmer, more elevated surface temperatures in the tropical Pacific. And during La Nina, in contrast, you have much less elevated temperature in the tropical Pacific. So that is the contrast that you see right there. And this contrast really drive a lot of changes, a lot of disruption, climate, a lot of disruption in the climate system across the globe. And that coupling that I talked about, you can have the rainfall. So this is an example again in the total rainfall January to March of 1998 when there was an El Nino, and here 89 when there was La Nina. You can see that rainfall is much more prominent in during 1998 than during 1989. So the coupling above normal sea surface temperature, above average rainfall, below normal sea surface temperature, below normal rainfall, and that is pictured here in the departure from normal. So that is really as simple as that. And we need to monitor the El Nino because of really its influence on the climate system around the globe. So when we do have an El Nino, we have divided actually the tropical Pacific into different regions from Nino 1 plus 2, 3, 3.4, and 4. And so when we have an El Nino, you can see the departure from normal is quite positive. This was the event of El Nino of 2015, 2016. And during La Nina, actually we're undergoing La Nina right now. It's still here. It's fading a little bit, but it's still there. So you can see also again the contrast between an El Nino event and also La Nina event, where now you have below normal sea surface temperature. And this one particularly have really longer for a long time because it started in 2021 and it's still ongoing. And we expect actually for it to continue at least through the fall of 2022. And we can look at the historical El Nino events. This is an index that we have created at our office at the Climate Fusion Center, where the orange is positive departures from normal, so El Nino years, and blue negative departures from normal. So this is the La Nina years. So you can go back in time and look at this data and see how it might have impacted past climate in your area of interest. But again, as I said, it's about the sea surface temperature, but also it's about the atmospheric conditions as well. It's a coupled system. So the way we monitor the atmospheric condition is an index that we call the Southern Oscillation Index. It's the difference in sea level pressure between the station of Tahiti and the station of Darwin. And when it is positive, that's what we shade here in blue, negative in red. So the blue is what we call the high phase, is associated with the cooling in tropical Pacific, and the red is the low phase that's associated with the positive sea surface temperature normal El Nino years. So El Nino years are associated with lower than normal Southern Oscillation Index, and La Nina years above normal La Nina years associated with above normal Southern Oscillation Index. So just for your information, and for really it's important because I know that a lot of people make that confusion once they see warming in the tropical Pacific, they say, here you go, we have El Nino. When conditions are really not there, the Southern Oscillation Index might not be showing it. Also, the rainfall pattern might not be showing it. So I just wanted to insist on that when we talk about El Nino Southern Oscillation, we're talking about both the oceanic component, but also the atmospheric component. So this is just the real-time monitoring of the sea surface temperature around the globe. And again, here we're looking at the current La Nina event. I didn't update this map, but even if I updated it, it will still show the same pattern. But you can see here below normal sea surface temperature across the tropical Pacific and warming in the maritime continent. That's the clear feature of La Nina event. If it were El Nino, it will be the other way around. It will be positive here and negative here. And oftentimes we do have a response of the Indian Ocean when it is negative here. It will be it's negative also over the Indian Ocean. So this is still a moderate, weak to moderate event. That's why we're not seeing that much response over the Indian Ocean. But the Indian Ocean also does have its own variability that also compete with El Nino. And this is just an evolution of the sea surface temperature anomalies across over several weeks. We do monitor this every single week. In fact, we do have a PowerPoint presentation that we issue to update ENSO state. But once we have done that now, how does ENSO impact, the climate system across the world? So this is just a regression, and I'm just showing October, December. It's showing you how really ENSO affects the rest of the globe. So this is regression and this is the correlation. So the correlations show you the strengths of the relationship between ENSO and the rainfall pattern. So you can see very clearly the areas where the ENSO signal is our strongest. That is the maritime continent, Southeast Asia, Northern Australia, but also in Africa, East Africa, Southern Africa, Northern South America. And then we do also see some signals in the United States, a little bit also in Europe, a little bit less in Egypt. And then this correlation show you actually the relationship, how strong it is. So the blue tell you that rainfall is negatively correlated with El Nino, and red tell you that rainfall is positively correlated with El Nino, and vice versa. So you can see that when you do have an El Nino event, for instance, you have enhanced rainfall activity in East Africa and below average rainfall in Southern Africa, and vice versa for La Nina. So this is very helpful because knowing the relationship between ENSO and rainfall help us really to predict. So here is just an example of prediction, experimental prediction from for Egypt, looking at the statistical model that is called canonical correlation analysis. And what you see here is the model performance. So red means that you have a positive skill, a reasonably good skill. And here we do see skill of 0.3 to 0.5, even for some locations, and it is cross-validated. So it is really a good skill. So because we use canonical correlation analysis, we are looking at the relationship between the predictive field, which is in this case the sea surface temperature, and rainfall. So you can see very clearly then how rainfall is related to sea surface temperature over the years for this period that have been considered. And you can see here that for this first mode, we do see a little bit of signal over the tropical Pacific, not much, but much of the signal is really in the West Pacific, also in the Indian Ocean. And actually, I would say also around the globe, the Mediterranean come out very strongly here, as you can see there. And this is the canonical time series associated with that, which really features some interannual variability in this relationship between sea surface temperature and rainfall in northern Egypt, in Egypt in general. So what this tells you is that in the first mode, the most dominant mode in this period that we have considered, so 30-year period, when we do have warming in the West Pacific and also Indian Ocean and the Mediterranean, actually, I would say actually warming across the globe, I would say, except for the tropical Pacific, we tend to have below average rainfall in the northern part of Egypt and in the southern part, well, below average rainfall in the northern part of Egypt and above average rainfall in the southern part of Egypt. So, but the relationship in north, the signal is not very strong, as you can see here. It's stronger here in the eastern part of Egypt than in the northern part of Egypt. But that's the first mode. Now, this gives you the second mode, which explain a little bit less of a variance than the first mode. But this mode here, though, really does show a clear ENSO signal. So that means that ENSO partially affect rainfall variability in Egypt. It's not dominant, but it does show in the data here in the second mode. And you can see here the clear ENSO signal with negative eigenvectors in the tropical Pacific, positive in the West Pacific, and negative in the Indian Ocean. So Indian response here is quite strong. And you see how it is related to rainfall. That is, when we do have negative eigenvectors in the predictive field, the SSD here that we have used correspond to negative eigenvectors in the rainfall. So that means that when sea surface temperature is below average in the tropical Pacific, then rainfall also tend to be below average in this area here, and vice versa. And this is the canonical time series associated with that. And if you look at very carefully, you will see that some of the El Nino years, not so prominent, can be retraced in this time series. So with that, so that's the statistical model, but we do have also the dynamical model, and this is just the North American Maritime Ensemble forecast system. And this is something that also we're making available to the public operationally. We have the regionalized calibrated NNME forecast that you can find on our website. And this is actually the current forecast from September, November 2022, going all the way to January, March of 2023. So this is for the globe. You can see there's the one for the globe, but also the regionalized. You can see them all on the website. Here, just a snapshot for Africa. And you can see that for the first season, that is September to November, the model is predicting below average rainfall over East Africa and above average rainfall over in part of the Sahel. You can see also prediction for above average rainfall in the end of Sahel. So the seasonal forecast are updated monthly, but my take is that these forecasts can be downscaled to really tailor the forecast to local areas. And I'm going to show you next just some examples of downscaling this forecast. So this is, for instance, the forecast for Central America, because this is also a region that we monitor very carefully for food security purposes. So you see the forecast over Central America here. And when we downscale it, the signal comes out very strongly, still using satellite rainfall estimates and driving a statistical model, canonical correlation analysis, by the way, with NNME prediction to make these forecasts. So I think that so that the users can really look at this and make more sense of it. And this is the downscaling of this particular region in Central America, but it could be also downscaled of a particular country or even a particular geographic location. So this is another example when we look at small island developing states. This is the Caribbean, for instance. This is the Eastern Antilles, and this is this is Jamaica. So here we're using gridded rainfall data at station locations and the NNME forecast to downscale at station locations. So that's also something that could be done, especially for countries, because they have access to rainfall data, so that they can use that rainfall data to downscale this NNME forecast to better meet the needs of their communities. Now, from the seasonal time scale, a little bit going to the sub-seasonal time scale. So predicting extreme events. So this is actually a case that my colleagues at EMA have given me, and I would like to acknowledge them, our TIF and Amira Square. I want to call them Amira Square, Amira Nasser and Amira Ibrahim. All three really were in the African desk and have kept in touch with me. Wonderful women, really very dedicated to their work and interested in the things that we do. So they provided me with this case that we looked at very quickly. Of course, Egypt is a bit tricky for me because it seemed like the station is mostly to the north, and if we don't have station data, it's very difficult. So we have to rely on satellite rainfall estimates. And in this case, we're using CMOF. So, but this was an event where they had a lot of rainfall in Egypt, more than 80 millimeters at several locations in northern Egypt. And actually, the satellite rainfall estimate depicted that very well. Except for the fact that, because satellite rainfall, much of the information is over the Mediterranean, but we know that this was happening also along the coast. So this is the rainfall excess above the 67th percentile. So really showing that this was really a great event, an extreme event. So then the question we asked was, can we predict this event? So again, this is the observation here, the rainfall excess above the 67th percentile, and how did the model do? So this is the week 2 consolidated forecast. The consolidated forecast is a combination of the NCEP Global Ensemble Forecast System, the NCEP CFS version 2, the Canadian model, and also the ECMWF. And you can see that the consolidated forecast was able to depict this excess of rainfall as well. A little bit less than observed, but still it depicted that. So, and this is the contribution of the different models from that I have just mentioned in terms of depicting the excess of rainfall. Of course, this is just one event. We need to look at many more events to make better sense of it. But also, more importantly, we need to have a good handle of the data set. Of course, given that much of the rainfall happening with northern Egypt, would be good to have station data or much higher resolution satellite rainfall estimates to really have a better sense of what is happening in the ground. But this is something that we are also developing in several parts of the world, Africa, but also Central America, Central Asia, and other regions where we monitor food security very carefully. So we use this forecast of extreme events. And then we integrated with the long-term monitoring of the climate system to make sense of what is happening, whether we have a drought that is developing, whether we have flooding that is ongoing and persisting. So every single week we update this map that we call the hazard outlooks for food security, This example is for Africa. We produce it also for Central America, for the Caribbean, and also for Central Asia. And we use, again, geographic information system to produce shapefiles for drought, severe drought, flooding. And then we share those shapefiles with our colleagues in the Famine Early Warning System Network. And those are social scientists that have also access to livelihood data. So the livelihood data include market prices, conflicts, nutrition, and so forth. And so that they integrate all the socioeconomic factors to provide these food security outlooks and highlight areas where food security might be a problem, whether they're going to be in stress mode or crisis mode or emergency mode. And so that information now, USAID uses that information to enact a plan, an emergency plan for releasing funds that can help prevent famine to occur. And USAID interest is just to locate the area that might have problem, work with NGOs, government organizations, and then really provide assistance for food or safe drinking water, and making sure that the people who live in those areas really do not undergo famine. So, so this is the summary of this presentation. African rainfall is marked by sharp variability, partially associated with the warming of the climate system and partially with natural variability. The El Niño Southern Oscillation, the Indian Ocean Dipole Mode, and the Atlantic Multi-Decadal Oscillation, all of these modulate rainfall variability on the interannual to multi-decadal time scale. So extremes in the African rainfall are associated with a planetary wave, the Julian oscillation, which I haven't had a chance to talk about, the North Atlantic oscillation, which I haven't talked about, that also induce changes within the rainfall season. So under a warming of the climate system, extreme events, drought, floods, have become more frequent with socioeconomic impacts, food security, health security. So numerical weather and climate models are now capable of predicting the changes in the weather and climate patterns, both for and within the seasons. So forecasts, weather, climate forecasts can help advance early warning and early action in various socioeconomic sectors. And we have proven that. We have been doing it for food security for nearly 40 years now. And now we are really starting to reach out to the health sector. And hopefully, if we can bring the right people at the table, we'll be able to advance the use of climate and weather forecast for health early warning system, whether in infectious diseases or non-communicable diseases such as heat health. Thank you very much. I look forward to some discussion. Thank you. Appreciate it. Over to you, Anjali.
Thank you, Wassila. Now, Dr. Ala will moderate the Q&A. You have given us so much food for thought, and I hope that we will have a good discussion on the results of what you have presented.
Thank you so much, Dr. Wassila. I really enjoyed this session, and I honestly learned a lot because I'm not an expert in this field, but I keep learning with each session Dr. Anjali helped us organizing. I would ask anyone who has a question to raise his hand or to directly unmute himself and talk, because we are running out of time and, and we want to take as much questions as we can. So, yes, I can see a hand. Dr. Yasmin, please go ahead.
Okay, thank you. Thanks, Dr. Wassila, for your interesting presentation. I have a question starting from the presentation about the heat index or the urban heat index. When you show us the result, I see you evaluate or give alert based on the precipitation and temperature. I was wondering if the relative humidity also entering how you assess the if it's comfortable condition or no, for example. So is it the relative humidity index on this or indicator in this or no? And another question is related to the heat waves itself. I was wondering also if how you give weight on this, because for example, if the temperature reached to 40 degrees in April, is it equal like if it happened in August or July, or you think we should give different weight on these heat waves? One last comment about the seasonal forecast, because I'm very interested with this product, and especially for extremes. In your opinion, how much certain we can depend on this? In terms of anomaly, based on my as a personal test I made it, monthly anomalies can give us, or in the seasonal scale, how much it warm, cold, or so. But in specific events is a little bit challenging. Or what do you think? How much we can depend on this? And thank you.
Thank you very much. Thank you for your question. Very interesting. I think that on the heat waves, the table I have shown, which has the maximum temperature, the rainfall, that one doesn't include heat index, but it's definitely a very good question. This is experimental. This is something that we started very, very, very recently. So for now, we're just using the maximum temperature and the rainfall, because if the maximum temperature meets the criteria, but there is rainfall, we know that the rainfall might temper, the impact of the heat. So that's why we say that, okay, this is no alert. But again, this is meteorologists sitting at their office and trying to figure it out. So it will be extremely important for us to go out and share this information with the health sector, and really for them to give us advice and let us know if indeed that is a good approach, or if we should take into account other consideration. So this is just a first step. And as I said, this is something that we started to do only about a couple months ago. So that's why your question is extremely important. And that is also why, for now, this product is just experimental, and we're working to improve it. We're also working to the same thing that we have done this table with maximum temperature. We are also working to bring in heat index where they would be able to factor the humidity into it. So happy to have a conversation with you on this if you're interested, and then see how we can move this forward. Because really our intention is to make this a global product. So I hope I have answered both questions on the heat. Now, in terms of rainfall and the prediction of extreme events, yes, that is an excellent question. I did show that case study of Egypt because I really don't have much to work with on Egypt. I didn't want to show example of other areas, because this is work that also we have done in different parts of the world, mostly sub-Saharan Africa, but also Asia as well. And those regions that we look at, those are regions where the climate signal is much stronger. So Egypt is a little bit more difficult because much of the rainfall is happening in the northern part of Egypt, and we really don't have much station data, at least for us at NOAA, to work with. And so I just quickly contacted my colleague at EMA, and they provided this event. So we cannot assess just based on this particular event. So that's why I said in my presentation that we have to look at cases. We also have to look at really the observation, the data, in order to really make good sense of this and see how skillful the models are in terms of predicting the extreme event. I can tell you that other regions that we have looked at, Southeast Asia and some parts of Africa, the model is very, very good in terms of depicting these extreme events. So is there anything else is there anything I have missed in answering your question? Please let me know.
Thank you so much, Dr. Wassila. We have a special thanks for you from Amira Nasser from EMA in Egypt. She's thanking you for your great presentation, and she's thanking you that she had the honor to work with you back in the days during her fellowship in NOAA. I would give the floor to Dr. Ala Khalil. He has a question.
Thank you, and thank you, Amira. Nice to hear those kind words, Amira. Thank you so much.
Thank you, Dr. Wassila, for your presentation. You are mentioned in your presentation about heat wave and health early warning. Do you have something for agriculture like heat wave and agriculture early warning to see the impact of heat wave on the agriculture and the crop production and what how much water we need?
Yes, that is also another good question, excellent question. And let me try to bring here the hazard outlook for food security here. If you look at the legend, here at the bottom we have abnormal heat, and that's what you see here. So it's very interesting that you have asked that question, because yesterday we had a team meeting and we were discussing the global heat hazards outlooks. The global heat hazard outlook, that experimental global map that I have shown, is really looking at extreme heat. We're looking at, like, you know, maximum temperature exceeding the 80th percentile. So in our hazard outlook for food security, which is more for agricultural purposes and maybe water resources, and you can see here, for instance, this drought of Southern Africa was associated with the big heat that we have highlighted here. So yes, we do look at abnormal heat in terms of agricultural crop impact on crops, but it's not the same. We don't look at it the same as excessive heat might have an impact on human health, in which case we're looking at really extreme heat. So that's the response, and I'm happy also to have that conversation further if there is an interest in that. Thank you.
Thank you so much, Dr. Wassila. Actually, I have a question. I'm coming from a medical background, so I would love to ask about the health heat wave warning system. I would just want to know, like, an overview. How can we do something like this here in Egypt? What's the steps that we can take to do it?
Another excellent question. I would love really to explore this with Egypt. I would love, and I mean it when I say it, because I do believe that heat waves are a problem in Northern Africa, and Egypt in particular, as we have seen on that map that I have shown. So I think that we are making progress in terms of heat wave forecasting. And we do have this forecast available actually real time. However, to advance this, to use them for health early warning, we have to work collaboratively with the health sector, not only the medical doctors, but also the people who work on the ground with health issues, you know, so other social scientists, epidemiologists, for instance, you know, behavioral scientists who understand, you know, how extreme event might have an impact on the population, you know, population vulnerability. So really, the pilot project that we're running in Senegal, to me, it's a vision, it's the way to go, where you have the meteorologists, the climate scientists working collaboratively with the health sector to integrate the forecast with vulnerability data. So that's what really will help you to reach out, to communities and to be able to advise populations that are vulnerable. The thing is that also we need to educate population. We need not only the people who are vulnerable, but also our decision makers, our policy makers. We need to educate them. There need to be a campaign of awareness, because I know this for a fact in sub-Saharan Africa, people go out their business and do what they need to do under the sun, working in the field, going to the markets and exposing themselves, to the heat and the consequences that might be associated with that. So we need to educate people, of the importance of this issue on the health of the people. And even myself, I didn't realize how heat can really have an impact on people until this past summer. In July, I was in Senegal with my daughter, who is very much American, born and raised in the United States. Even though she's been in Senegal many times, we had a very, very, very hot period in Senegal. And I was in downtown walking with my daughter, and all of a sudden, she was really having issues, feeling discomfort, really getting disoriented. And this was nothing but the heat. I just like, oh my gosh, this is something that I'm seeing now even happening to my young daughter, but who is very much American and is not really used to this extreme heat that we were undergoing. So there is work to do here a lot. And I'm glad that you have asked that question. Being a medical doctor, coming from medical background. So we are trying at NOAA to really bring institutions together, to really try to advocate for advancing the use of weather climate information on health early warning. In fact, we are organizing a conference in Washington, D.C. in May of 2023, focused essentially on this. And Julie's program, the National Science Foundation, has already provided funding for this conference. And there are several other organizations, the World Meteorological Organization, the National Institute of Health, the Gates Foundation, who have really also funded us for this conference to happen. So I have submitted a proposal for the U.S. Senate at the COP27 that's going to happen in Egypt, where also, if approved, I'll be talking about this issue as well to try to promote this work that we're trying to do. So if there's interest in Egypt, I would be more than happy to sit down and talk to you guys and see how we could try to advance this in Egypt as well. Thank you. Over.
Thank you so much, Dr. Wassila. I think we can actually work on this in COP27. So please let us know once you put a leg in Egypt to start working on that. We have a couple of questions in the chat box, and I would ask you kindly to answer them a bit quickly. The first question is regarding the definition of heat waves. It varies from a place to place in terms of temperatures above average and the number of days. And if it's different, how will I determine it for Egypt?
Yes, that's also another good question. I think that there are several definitions of heat wave in the literature. For us, for now, we use maximum temperature exceeding the 80th percentile for 3 consecutive days, or heat index exceeding the 80th percentile for 3 consecutive days. You could look at it for 2 consecutive days. You can look at it for just 1 day. It's just something that, again, for any particular location, we have to come together as a multidisciplinary team to agree on how we want to define heat waves. But whichever way we define it, what we have shown is that our models are capable opportunities at heat events. Now, the nice thing about using the percentile values is that it is not actual temperature dependent. Because the 80th percentile in Canada may be actually 25 degrees Celsius. And that would qualify for the heat wave event because the people who live there are not used to living temperature at 25 degrees Celsius. If you go to Sahel or to Egypt, Southeastern Egypt, that 80th percentile may be 40 degrees Celsius or even more. So that's the nice thing about using the percentile, because you talk about really excessive heat for any given place. Thank you.
Thank you. We have another question. If we can make a risk index interactive map to relative sectors in the future based on the data that you presented today?
I'm sorry, I didn't get that question. Could you say it again?
Dr. Mu'tasim, okay, it is the question from Dr. Mu'tasim al-Tawil regarding if we can make a risk index interactive map to relative sectors in the future based on these data.
Okay, well, relative sector, it depends on what sector too, right? So what applied to heat health may not apply to agriculture, for instance, as the gentleman has asked earlier. So it really depends on the sector that we're looking at and what is the influence of these extreme events on that particular case. So it's something that we have to look at and see what it is. But definitely, in terms of excessive rainfall, for instance, or drought, we're also planning on doing, that interactive or providing that interactive map for drought alert, for flood alerts. And actually, our vision is not to just stop there, but to make an application where people can access this information on their cell phone, on their iPad, wherever they are. They can just click and see what is happening. So that is our vision moving forward. For drought, heat health, and also flash flood. Thank you.
Thank you. We have another question regarding the difference between health risk and health hazard.
Yes, well, it is nuanced, right? We use heat hazards. Heat hazard is just the climate component, right? Mm-hmm. The forecast of the heat wave, we say, okay, these are the heat hazards outlooks. There is a danger for heat to occur. And then we use the heat health risk to health. Health is based on the heat hazard outlooks. So health risk, heat hazards. That's how we look at it.
Thank you so much, Dr. Wassila. And again, Amira is thanking you for your efforts to work on making a prediction tool for Egypt. We know that you have reached out to the EMA to develop a tool for Egypt. So she's acknowledging that and thanking you so much for helping in doing so. And they are currently trying to connect you with the necessary stakeholders, especially in her health sector, of course, as you said, to develop the health heat wave or heat waves early warning. I don't want to take much of your time. This has been a very interesting session, probably the most interesting one since we started this series. Thank you so much for your time. And of course, thank you to Dr. Anjuli for helping us in arranging these sessions for the CCIC. I don't know if you need anything else from our side, just please let us know. And I would love, of course, to thank Dr. Mohammed Fahim and Dr. Ala Khalik for their hospitality, for hosting us here today and for every day for a month now. Thank you so much. And for any more questions, you also will have the email for Dr. Wassila in case you want to reach out directly to him. Dr. Wassila, do you want to say anything else to us?
Allah, I cannot thank you enough. Really, you and Anjali for enabling this to happen. Really, it's something I'm very, very, very passionate about. And I really hope that this has triggered some interest and, that we can have a conversation moving forward in terms of advancing the use of climate information for health early warning, non-communicable diseases, but also infectious diseases. So I really thank you from the very bottom of my heart. Thank you to all who have asked questions and comments, and please do feel free to share this presentation with everybody who has attended this meeting today. And anyone has a question, please feel free to reach out to me. I'd be happy to answer. So thank you so very much for everything. Thank you.
Thank you, Wassila.
Thank you
so much. Have a nice rest of the day. Thank you.
Thank you. You too. Take care. Bye. Bye-bye.
Bye-bye.